Remember, electricity is dangerous. Always make sure you're properly trained before working with electricity and electrical equipment. PID control is everywhere: temperature controllers, motor drives, even cruise control. But do you actually understand what those three letters are doing? Not the definition, but what's physically happening in your system. Today, we're going to make PID finally make sense. In this video, you'll learn what a feedback loop really is, what PID control actually does, what P, I, and D mean in simple terms, how a standalone PID temperature controller heats water. So what is a feedback loop? A feedback loop is when a system continuously measures its output using a sensor, compares that measurement to a desired set point, and then makes a correction if there is a difference. After the correction, the system measures again. This cycle of measure, compare, and correct repeats continuously to keep the system stable. In our setup, we're heating water. A thermocouple measures the water temperature and sends that signal to the PID controller. The controller compares the measured temperature to the set point. If the temperature is below the set point, the controller turns the relay on, which energizes the heating element and starts heating the water. As the temperature gets closer to the set point, the controller adjusts the heater operation to keep the temperature stable. The thermocouple then measures the temperature again and sends the new value back to the controller. So the system is constantly measuring, comparing, and correcting. And that continuous cycle is what we call a feedback loop. In this example, our set point is 110 degrees Fahrenheit. Now we know how the feedback loop works. But the real question is, how does the controller know how much heat to add? That's exactly what PID control determines. But before we dive in, we'd like to ask for a small favor. If you haven't already, please take a moment to subscribe to the channel. And while you're at it, don't forget to hit the notification bell so you never miss an update, and give this video a thumbs up if you find it helpful. Your support really helps us grow and keeps us motivated to bring you more valuable content. PID stands for proportional, integral, and derivative. These three control actions work together to reduce the difference between the set point and the actual process value. In this video, we're not going to worry about the math or formulas behind it. What really matters is understanding what each part actually does in the system. Most modern PID controllers, whether they're standalone controllers or PID loops programmed in a PLC, can auto-tune themselves, which means they automatically determine the best P, I, and D settings for the process. So instead of focusing on the math, let's focus on what each part of the PID controller is doing to control the process. Proportional control reacts to how far the temperature is from the set point. When the water is far below the target temperature, the controller keeps the heater on most of the time. As the temperature gets closer to the set point, the controller begins turning the heater on and off more frequently. So even though the heater is only on or off, proportional control adjusts how long it stays on. If we only use proportional control, the system will usually oscillate around the set point. The temperature may go above the set point, then drop below it, and continue repeating this cycle. This creates overshoot and undershoot, where the temperature keeps swinging up and down instead of settling at the target value. If those swings are large, the system becomes unstable and inaccurate, which is why proportional control alone is usually not enough. And that's where integral and derivative control come into play. Integral looks at the error over time. If the process keeps going above and below the set point, the integral action slowly adjusts the controller output to reduce that repeated error. In other words, it keeps track of how long the system has been off target and makes gradual corrections to push the process closer to the set point. This helps reduce the continuous overshoot and undershoot, allowing the system to settle closer to the desired value. While integral looks at error over time, derivative looks at how fast the process value is changing. If the temperature is rising quickly toward the set point, derivative action reacts to that rate of change and reduces the controller output early. This helps slow the system down as it approaches the set point, reducing overshoot and making the process settle more smoothly. Now that we understand what PID does, let's look at our setup and see how easy it is to program the controller. First, we need to set the set point value, or SV. To do that, press the Set button and the SV will begin flashing. Then adjust the value to your desired set point. For our setup, I'm going to set it to 120 degrees Fahrenheit. Next, we'll enable Auto-Tune. Once Auto-Tune is activated, the temperature display will begin flashing. The controller will then start automatically tuning the PID parameters for the process. When the flashing stops, that means the auto-tune process is complete. Notice that when the process temperature is far from the set point, the relay stays on continuously. As the process variable gets closer to the set point, the relay begins turning on and off. This allows the controller to regulate the heat and maintain the temperature at the set point. Sometimes you may need to run auto-tune a couple of times to get the best results. And if something in the system changes, like replacing the heating element or adding insulation to the tank, the process will behave differently. So it's a good idea to run auto-tune again. Thank you for watching. If this video helped you understand PID clearly, give it a thumbs up and subscribe to Electrical Lab for more simple videos on electrical controls, hydraulics, and pneumatics.